Jnanam paramam dheyam. Knowledge is supreme.
Okay, so some familiar data with just to corroborate what I said formally. If suppose you take both the particles to have the same angular momentum, like two spin half particles or two spin 1 particles, let me call the angular momentum of particle 1 and particle 2 to be A. The total J maximum will be 2A, which is J1 plus J2. Minimum will be J1 minus J2, which is 0, and it goes in steps of 1. So this is the range of the coupled basis angular momentum. It is not a fixed value, it goes from 0 to 2A. If one angular momentum is orbital and the other one is spin, then what is the range? Spin is just half, spin half. J1 plus J2 is L plus half. You have to go in steps of 1 to J1 minus J2, which is L minus half. The difference between these two is only step of 1. So only two possibilities. The total angular momentum J, when you couple angular momentum, orbital angular momentum to the spin half, there are two possibilities for the J. If both are spin half, by the same argument, if you put A to be half, then it is 0 or 1. So now what we will do is, for the let's take the simplest one, which is two spin half angular momentum addition, and look at what is the CG coefficient for two particles which are spin half, which is coupled. So just to recall, uncoupled basis, it's a 4-dimensional. One spin half is 2-dimensional, another spin half is 2-dimensional linear vector space. The tensor product of two spin half will give you a 4-dimensional vector space. And we can write the 4-dimensional vector space, all the basis states. What are the possibilities? M1 is half, M2 is half. M1 is minus half, M2 is half. M1 is plus half, M2 is minus half. What is the last one? Both being minus half. This is also important when you do quantum computers also. So let me just, so we can write formally, we can suppress the J1 and J2, write up, 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 down, down, up, and down, down. This is the uncoupled basis. Okay, I am not going to put J1 and J2, which is half half, but we can just remember that for two spin half. I am only writing the M1 and M2. I am not writing the J1 and J2. What about coupled? Coupled, what are the possibilities of J? It is two spin half, 1 and 0. So coupled basis will be J equal to 1 and M equal to 1. J equal to 1, M equal to 0. J equal to 1, M equal to minus 1. Anything else? J equal to 0, M equal to 0. Interestingly, this is what we expect also. The dimensionality of the uncoupled basis should be same as the dimensionality of the coupled basis. This is 4-dimensional. This is 4-dimensional. So this should be related by a matrix which is 4 cross 4 matrix. This is CG matrix. We are interested in finding the CG matrix. The first element here is 1, 0, 0. You agree? This state is a stretch state. This is a stretch state. I said that the coefficient of this is 1. provided M1 plus M2 is M equal to 1. Others are all 0, so these are all 0 in the 4 by 4 matrix. Now we need to work out the other 3 rows. Okay, so here just for explicit things I have written the half, M1 and M2, the quantum numbers, rather than putting the arrows, but you understand. So these are the 4 states, and the maximum state, which we call it as a stretch state, M equal to 1 and S equal to 1, that's going to be exactly this. So that gives you the coefficient or the first row, which is 1, 0, 0. Then the next thing is, we need to do one step lower than M maximum. M maximum is 1, right? The next one is M equal to 0. So M equal to 0 can be obtained by acting lowering operator on both left hand side as well as right hand side. But the lowering operator here will be the lowering operator in the coupled basis, and the lowering operator here will be the uncoupled lowering operator. So that is a very important thing which you should remember. So how do you do that? Can you try it? Left hand side is similar to any SM, the lowering operator. I am going to suppress the J1 and J2. I am writing only the coupled state, which is Jm. This will be tell me J plus M into J minus M plus 1. Is that right? Am I right or wrong? So J minus on J equal to 1, M equal to 1 will be so this is the left hand side. But I have already told you that J equal to 1, M equal to 1 is a stretch state with the plus 1 coefficient, which is going to be M1 equal to half, M2 equal to half. Right? Or both are up states. On the right hand side, if I want to do the lowering operator, I have to do it as if I am working on the uncoupled basis. The lowering operator there will be J1 minus cross identity plus identity cross J2 minus. You have to do that on up state. State will be, what is this coefficient? So you should remember this 1 and 2 I am just putting to know it should operate on the first state and it should operate on the second state. As an operator, it's just a lowering operator. Okay. What will this be? Some coefficient times. It is identity on the first state and the lowering operator on the second state. That's why I am putting this notation. Sorry. This notation. What will that be? Coefficients of both are 1 because your J1 and M1 are half and half. So half plus half will be 1. Okay. So this is 1 and this is 1. But you have to sum up both. We had J equal to 1, M equal to 1. We had an S minus operator or J minus operator. This has to be J1 minus cross identity plus identity cross J2 minus. This has to operate on M1 equal to up spin and cross product with M2 equal to up spin. You all agree? I am writing in all possible notations so that you get familiar with everything. Uncoupled basis is a tensor product of two states. This is another way of writing. This we have already done. This side is square root 2, j equal to 1, m equal to 0. This side, H cross. Thank you. Yeah. And this side is going to be up down plus down up with a H cross. We did this separately. The first one we operated on the state and we got down up. The second one we operated on up down, up up, which gave you up down. But it's a sum of these two operators. You have to take the sum of those two states. So what do? We need to find out j equal to 1, m equal to 0. That state is 1 over square root 2. Take the square root 2 outside from here below. Remove the h cross on both sides. Times up down plus down up. So this side is a coupled state. Coupled state can be written as a linear combination of the uncoupled basis, and that coefficient should give me the CG coefficients of the CG matrix. So let's write the CG matrix again. You have to help me. So I am going to put here M1, M2, this side, and this side let me put J and M. So M1, M2 is up up, up down, down up and down down. Clear? So let's write the state as j equal to 1, m equal to 1. J equal to 1, m equal to 0. J equal to 0, m equal to 0. I'll tell you why I am doing this. J equal to 1, m equal to minus 1. Both the m equal to 0 can happen for both j equal to 1 and j equal to 0. I'm just putting it together. The j equal to 1, m equal to 1 contribution will only come from m1 plus m2 equal to m. Only this one. That's the stretch state. So this element is 1. Others are all 0. J equal to 1, m equal to 0 we have written down is 1 over square root 2 times up down plus down up. So which means this is 0, this is 0, this is 1 over square root 2 and 1 over square root 2. What about j equal to 1 and m equal to minus 1? Which one will contribute? Will this contribute? Will this contribute? Why it won't contribute? m1 plus m2 should add up to minus 1. Which is the only possibility? This one. So this is the lowest stretch state. That also I can put it to be 1. What about j equal to 0, m equal to 0? I want m equal to 0. I cannot get m equal to 0 from both up, right? This is 0. You all agree? This is also 0. But this I can fix it as a and b. How do I fix this A and B? If I call this to be a complete set of bases, I would like my J equal to 1, M equal to 0 to be orthogonal to J equal to 0, M equal to 0. So that is what will happen, right? So that is what will happen. So that will fix us. There can be some phase factors and stuff like that, or the sign factors. You could fix one convention and write it this way. So up to a sign, these two are correct. So this way, I have actually showed that J equal to 0, M equal to 0 is 1 over square root up down minus 1 over square root 2 down up. The left hand side is a coupled state, right hand side is in the uncoupled basis. Only these two states will contribute to the state, and this has to be orthogonal to the J equal to 1, M equal to 0 state. Okay. So as an exercise, we have also checked that J equal to 1, M equal to minus 1 is down, right? But you can also do independently, just to make sure that in whichever way you do it, it should not give us a wrong result, right? So you take J equal to 1, M equal to 0 and operate your S minus or J minus operator. What will that give you? Something, coefficient, J will not change. What will change? M will become minus 1. Okay. What is that coefficient? Yeah, what is this number? Root 2 H cross. So do the same thing. J equal to 1, M equal to 0 is actually 1 over square root up down plus down up. On this you operate your J1 minus cross identity plus identity cross J2 minus. Do this. What do you get? If you do a minus on the state, it will make it down. So it will become down state. But if you do a J2 minus on the state, it is 0. Can't go below. But if you do the J2 minus on this state, it will make it down. J1 minus will not act on it. So it is going to be some coefficient times down. And then you compare. And then what do we get? J equal to 1, M equal to minus 1 is down with plus 1 coefficient. Please check this. I argued by the lowest stretch state to be coefficient 1. You can also do it by the ladder operation and you can show this. I have not done the in-between step, but please do it. So now CG coefficient looks interesting, easy. So M equal to 0 can be obtained by acting lowering operator on LHS and RHS. LHS is the stretch state, RHS is also the stretch state in the uncoupled basis. You do S minus as S1 minus. I am just summarizing for completeness. You can do the S minus on the coupled basis, lowers it to M minus 1 with this coefficient. Sorry, I forgot the H cross. Please plug in the H cross. So there will be a square root 2 times H cross here. We have done this on the. So and do it on the uncoupled basis. I am not putting the cross identity cross, but you remember this. So this one will lower half to minus half and this one will lower the second half to minus half. So it is sum of those two states. And using this, we have written the uncoupled state, which is with the magnetic quantum number as 0, can be contributed by M1 and M2, which are two possibilities. And it is the sum of those two with the coefficient 1 over square root. Is it normalized? It's normalized. So it becomes automatically normalized because we have taken care of that even in the construction. Okay, because the left hand side coupled states, whenever I wrote those coefficients, they are also normal. Acting lowering operator, you can still do the lowering operator on LHS again and RHS, which we have derived now. And what will we get? We will get that the 1 minus 1 is exactly with coefficient 1. How do we determine J equal to 0, M equal to 0 is the question. That also I said that J equal to 0, M equal to 0 has to be orthogonal to, must be orthogonal to all these states. The only state which it has overlap is only with the 1, 0 state. We can check the orthogonality there. These things are trivially orthogonal because this one contribution is with some 2 up spins. This contribution is from 2 down spins. Whereas to get a 0, you need 1 to be up and 1 to be down. So there is no way, they will all be orthogonal. If you need to only check that this is orthogonal to the different J but the same magnetic quantum, which is what we did for this case. Okay. Okay. So I said that you have to make sure that they are orthogonal, and that fixes the coefficients have to be 1 over square root and minus 1 over square. There is something which I want to ask you in these two states. If you look at the J equal to 0, M equal to 0 state, if I interchange M1 and M2, is the state symmetric or antisymmetric? It picks up a negative sign, right? So J equal to 0 state, which is composed of 2 spin half composite. The singlet state, or J equal to 0, is sometimes called as a singlet state because it has only one component. That state is an antisymmetric combination of the uncoupled magnetic quantum numbers. It's M1, M2, where if it is M1 is up and M2 is down, if you interchange, you pick up this negative sign. What about J equal to 1 and M equal to 0? It is symmetric. Okay. Another way of seeing that J equal to 1, M equal to 0 has to be symmetric is that the ladder operation on a stretch state is always symmetric, right? Both are. So on a stretch state which is symmetric, if you do the ladder operation, you will always get symmetric states. You will not get antisymmetric states. There is no way you can get antisymmetric coefficients. Okay, these are some things which you will see in particle physics, that they will kind of control how to fix this angular momentum conservations and so on. So just keep it in mind that it has the orthogonal state is an antisymmetric state, J equal to 0, M equal to 0, and J equal to 1 and M equal to 0 is obtained by ladder operation on a symmetric state, it will remain symmetric. Okay.